Hello everyone, today I'm going to explain infinite series, summation notation, and the integral test. The main question of this presentation is simple. How can we determine whether adding infinitely many numbers produces a finite result? We obviously cannot add an infinite number of terms one by one. Instead, we study limits, partial sums, and improper integrals. By the end of the presentation, we will have a clear procedure for deciding whether certain infinite series converge or diverge. A sequence lists terms, a series adds them. First, we need to understand the difference between a sequence and a series. A sequence is an ordered list of individual terms. For example, if a sub n equals 1 over n, the sequence is 1, 1/2, 1/3, 1/4, and so on. A series is created when we add the terms of a sequence. Therefore, the corresponding series is 1 plus 1/2 plus 1/3 plus 1/4, continuing indefinitely. This distinction is important. A sequence studies the behavior of the individual terms, while a series studies the behavior of their accumulated total. Sigma notation compresses a repeated addition. Sigma notation is a compact way to represent repeated addition. The Greek letter sigma means that we must add a collection of terms. The expression below sigma identifies the index and tells us where to begin. The number above sigma tells us where to stop. Finally, the expression to the right gives us the rule for generating each term. In this example, k begins at 1 and ends at 5. And every value of k is a square. When we expand the notation, we obtain 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, which equals 55. For an infinite series, the upper limit is infinity instead of a final number. Convergence belongs to partial sums. To define convergence, we use partial sums. The partial sum S sub n is the sum of the first n terms of a series. For example, S sub 1 contains only the first term, S sub 2 contains the first two terms, and this process continues as n increases. If the sequence of partial sums approaches a finite number L, the infinite series converges to L. The graph shows that the partial sums of 1 over n squared approach a horizontal limit. However, we must remember an important warning. The condition of a sub n approaches zero is necessary, but it is not sufficient. If the terms do not approach 0, the series definitely diverges. But if the terms do approach 0, we still need another convergence test. Conditions for the integral test. The integral test cannot be applied to every series automatically. First, we must find a continuous function f of x such that f of n equals the term a sub n. Then we must verify three conditions. The function must be positive, continuous, and decreasing on the interval from 1 to infinity, or at least after some starting value. If these conditions are satisfied, the series and the corresponding improper integral have the same convergence behavior. This means that they either both converge or both diverge. However, the series and the integral do not normally have the same numerical value. The test only tells us whether they converge or diverge. Why the integral test works? This diagram explains the main idea behind the integral test. The terms of the series can be represented by rectangles with a width of 1. The improper integral represents the continuous area under the curve. Because the function is positive and decreasing, the rectangles can be placed consistently above or below the curve. As a result, the tail of the series is trapped between two improper integrals. The integral on the left provides a lower estimate, while the integral on the right provides an upper estimate. If the improper integral has a finite area, the corresponding series also has a finite total. If the integral grows without bound, the series also diverges. This comparison between discrete rectangles and continuous area is the reason the integral test works. Example with 1 over n squared. Now we will apply the integral test for the series from n equals 1 to infinity of 1 over n squared. We choose the function f of x equals 1 over x squared. This function is positive, continuous, and decreasing for x greater than or equal to 1. Therefore, all the conditions of the integral test are satisfied. Next, we evaluate the proper integral from 1 to infinity of 1 over x squared. We replace infinity with a variable upper bound p and take the limit as p approaches infinity. The antiderivative of x to the negative second power is negative 1 over x. After evaluating the antiderivative, we obtain 1 minus 1 over b. As b approaches infinity, 1 over b approaches 0. Therefore, the improper integral equals 1. Because the improper integral converges, the series also converges by the integral test. It is important to understand that the series does not equal 1. Its exact sum is pi squared divided by 6. The integral test proves convergence, but it does not calculate the exact sum. The harmonic series. Now let us consider the harmonic series, which is the sum of 1 over n. The individual terms of 1 over n approach 0. However, this does not guarantee that the series converges. We choose f of x equals 1 over x. This function is positive, continuous, and decreasing for x greater than or equal to 1. The corresponding improper integral is the integral from 1 to infinity of 1 over x. Its antiderivative is the natural logarithm of x. After evaluating the integral, we obtain the limit of the natural logarithm of p as p approaches infinity. The natural logarithm continues growing without bound. Therefore, the improper integral diverges. By the integral test, the harmonic series also diverges. This example proves that terms approaching 0 is not enough. The terms must approach 0 sufficiently quickly. The p-series rule. The previous examples lead us to the general p-series rule. As p-series has the form of the sum from n equals 1 to infinity of 1 over n to the power p, if p is greater than 1, the series converges. If p is less or equal to 1, the series diverges. The boundary case is p equals 1, which produces the divergent harmonic series. For positive values of p, this rule follows directly for the integral test. If p is 0 or negative, the terms do not approach 0, so the series diverges immediately. The exponent determines how quickly the terms decrease. They must decrease faster than 1 over n for the series to converge. Final procedure. To summarize, we can apply the integral test using 4 steps. First, match the term a sub n with a continuous function f of x. Second, verify that the function is positive, continuous, and decreasing. Third, evaluate the corresponding improper integral by writing it as a limit. Finally, transfer the conclusion from the integral back to the original series. If the integral converges, the series converges. If the integral diverges, the series diverges. The central idea is that infinite addition becomes manageable when we style limits and comparison instead of attempting endless arithmetic. Finally, remember the most common mistake. A sub n approaching 0 is necessary, but it does not prove convergence. The harmonic series is the clearest counterexample. Thank you.